I would now like to invite Dr. Gulab Singh, Associate Professor, Indian Institute of Technology, Bombay, to share his expert talk on radar polarimetry methods for geo-environmental studies. Dr. Singh is a recipient of numerous awards, such as University Grant Commission Fellowship, Japan Society for the Promotion of Science, JSPS Postdoctoral Fellowship 2014, and the UNESCO Scientific Grant Award 2007, to name a few. We look forward to your session. Welcome, sir.
Good afternoon to all. So thank you very much for nice introduction and suggesting my topics. So I'll move on without naming my topic. Okay, what are the contents I'm going to talk here? Okay, so generally radar polarimetry, we look forward how the polarization measurements and analyzing we are doing through the radar measurements. So why it is required? So because suppose you have a single polarization measurement, transmitting edge, receiving edge, you will get such kind of image. Okay, so it will be very difficult to interpret if you would like to interpret. And suppose you have the another option of the polarizations transmitting V, receiving V, so you will get that VV polarization. Another case, you can have that cross polarizations capability to get that polarization measurement. Suppose transmitting H, receiving V, or V transmitting, receiving H, depends on that what is the configuration of radar system. So here you have seen the three kind of images which is showing that individual polarizations measurement. If you look at that interpretation, it's very hard to interpret any images. But if suppose you have a system like which is providing simultaneously all three images, and you combine or you extract some useful information in terms of scattering, that will helpful for monitoring, interpreting, analyzing, inverting your geophysical parameters. Like one example I'm showing here, in case suppose you have that multipolarization images, so you can look at here. So you combine and extract the different scattering phenomena. For example, surface is representing by the blue color, double bounce is representing by the red color, and volume represented by the green color. So generally, these are the major representation of the surface features in terms of like vegetation, in terms of that water body, bare soil, or urban area. So if you continuously monitor this one, this will also help you to understand the changes on the Earth surface, which can be translated or interpreted in terms of the environmental change. Okay, whether you are looking forest application, looking for the urban sprawl, urban damages, or you are looking for flood monitoring, you are looking for crop damages. Okay, so several applications are there based on this scattering interpretation. So this presentation will focus how we'll understand, how we'll extract the scattering information, and then further how to interpret for particular targets. Okay, so outline of my presentations will be like what is the polarization measurements, and what are the methods which can help us to extract such features or information which will be useful for interpreting the data, and few applications of that interpretation of the data. And then I will conclude my talk. Okay, so as you know that you have seen the previous presentations, so Earth surface parameters monitoring is very, very important or crucial for monitoring the health of our Mother Earth. For example, you look at flood monitoring, other damages. So it's very important. And you need a like 24/7 service. It's not like you depends on like once a while you do. So you need a regular monitoring. So in that way, radar remote sensing is like complementary to that optical remote sensing. And if suppose you have that advanced radar remote sensing techniques, for example, we have that all polarization combinations, measurements with the radar system, then it will very good. So here this entire talk is related to that advancement of the SAR system with the polarimetric measurements, and we look here at how to utilize those information, because the motivation is here. Now most of the agencies are planning or planned in the past with the fully polarimetric radar system. So we need to have such kind of expertise or kind of knowledge how to utilize those data and how it is going to be beneficial for our society. Okay, so these are the few example of that full polarimetric synthetic aperture radar data sensors or system or satellite. Few are spaceborne are listed here and few are airborne. Okay, so spaceborne generally right now we have a single frequency independent radar system. For example, TerraSAR X or Tandem X working on X band. Radar set 2 or it's working in a full polarimetric mode. So operational, you can choose single, dual, and polarimetric, but it is in C band. And another is ALOS, which is like work from 2006 to 2011, and that in from 2014 onwards, that ALOS 2 or Pulsar 2 is there, which is also giving the good images in L. So we don't have at present in space any multi-frequency SAR system with multiple license capability. But in future, our NISAR system, which is like NASA ISRO joint collaborations, satellite mission will come up, and which will provide at least dual frequency data in a polarimetric mode. That will be very great advantages for Indian users as well as others. So, but few like sensors are available which are providing multi-frequency data simultaneously. For example, this EPSAR, which is the sensor or systems from the DLR, German Aerospace Agency, you can get simultaneously 3 frequency data. Okay, either you take the LC X band, take C X P band, depends on your choice. But we can take maximum 3 frequency data simultaneously. So it's one. Okay. So we hope that in future we will have a similar kind of multi-band data, like in a spectral mode, optical multi-spectral data. So we will have the multi-frequency, multi-polarization data from the future. Okay, so but right now what I'm going to talk here, what we have at present, we are looking for that one. So generally we get that polarimetric data or SAR data in terms of the different polarization capability. So it is single frequency, but it's suppose you have a single frequency, single polarization, it's very difficult to interpret, as you learned in the very first slide. So here, if you have that multipolarization data that we can treat as a channel for different bands data, different channel data, but it is different from the optical kind of measurements. Right? So this radar generally gives us data in terms of the complex form, A plus IB form, and this radar data measures the amplitude of the signal and phase of the signal, which is generally we get that only intensity data from the optical. We don't have generally phase information from the optical data. So by this utilizations of the phase and amplitude data, we can do several applications. So if suppose deal with only polarizations based intensity data, you can look at this radar polarimetry image interpretation. If you look at this only phase information, absolute phase information, then you can do some interferometry. So here you can also divide into 2 streams this radar remote sensing. So further, if you combine both, you can also do pole-SAR interferometry combined. So you can do the pole-in-SAR, polarimetric interferometric synthetic aperture radar, which is useful for monitoring height, monitoring better classification. So there are several applications. But here I am restricted to this presentation on polarimetry measurements and applications. So suppose you have the radar system is transmitting a signal and interacting with the target, and you have the suppose incident polarization is horizontal after the interaction of the target. So you will not have the guarantee it will come back in a horizontal polarization. It can be anything. Depends on that your receiver. Suppose you have the combination of receiver horizontal and polarization. So you can get either H or V. So you will get 2 possible combination of the polarization intensity, HH or VH, depends on that which one you are transmitting. Suppose you are transmitting H, receiving H, transmitting H, receiving V. So you will get HH, HV. Or suppose you are transmitting a switch to that another polarizations, vertical polarizations interacting with the target, then same scenario, no guarantee it will come back in a vertical polarizations. So depends on that target property, that polarization orientation shift. So with this configuration, we can get 4 possible combinations: HH, HV, VH, and VV. And we can write those measurements in a 2x2 matrix. Okay, and this 2x2 matrix have like 4 amplitude, 4 phase information. So 8 total information, independent information, if you have that transmitter and receiver separately. But in case suppose you have that transmitter and receiver, generally we have the monostatic, same radar antenna can transmit and receive, depends on the switch. Okay, so that we can reduce some of the measurements because of the reciprocity. HV we can put equal to the VH. So in this way we will get only 6 independent information here. But that is absolute scattering matrix. Okay, but we don't look here for absolute phase. Absolute phase is important for the interferometry. We look only relative phase information. Now, how to get that relative phase information from the S matrix? Either you can get that's one of the phase common from the S matrix, you can get the relative S matrix, or another way to get it, you can go to the higher order statistics of the scattering measurements or radar measurements, like convert from S to C matrix, covariance matrix, coherency matrix, or other matrices. So you will automatically get this power matrix, which have only relative phase, not the absolute phase. So we can get one of the matrix and apply the methods to extract the different scattering phenomena. Okay, so that one of the example is there. How can I hide this bar from here? Okay, so like I told you that you can reduce that independent number due to that monostatic case. So it will remain only 6, but you are taking one of the phase outside common and just taking that only that relative matrix. So this will be the this is representing your relative phase information along with the amplitude, 3 amplitude, 2 relative phases. So total 5 independent will be there in relative S matrix, or means scattering matrix, which will get from the radar data directly. But you can also convert into the second order statistic, because that will represent some more depolarization phenomena, and it's a very good representation, because that coherency matrix has coherency matrix element has some physical interpretation directly to the target or physical word target. Okay, like for example, SHH plus SVV combination represents, or you can say it's representative of surface scattering. Next one, SHH minus VV modulus square representative for the double bound scattering, and HV generally comes from the depolarization phenomena. It can happen from the vegetation mainly. It can also come from the glacier or some oriented urban area. So these are the such kind of that physical interpretation of T matrix elements. So it is always good to use this T matrix, although you can use any other matrices and the result will be same at the end. Right? The other advantages of that conversion of S to T matrix, because it is representing second order statistics or polarimetric information, and it's easy to unitary transform. Okay, so when you are doing some mathematical operation, that is also easy to follow with the T matrix. Okay, now you have the question like you have that S matrix measurement. So like suppose you have the 4 polarimetric combination measurements from the radar, and that we are putting in S matrix, and from the S matrix you are converting T matrix. Now, what is the use of this one, and how it is useful for getting that target information? Okay, so this is like a mathematical form of the T matrix, but it has a significant physical information. Okay, as I told, each elements have some physical relation with the target, surface scattering, double bond scattering, and volume scattering, like depolarization phenomena. Okay, if suppose we have this T matrix and we split this T matrix in a sub matrices, like which is representing like surface scattering model, double bond scattering model, volume scattering, and other kind of scattering information, then this scattering information can be utilized for image interpretation. As you have seen earlier, if suppose you have the surface double bounce volume, you can interpret easily where the volume is getting dominant. You can relate with the vegetation, where that double bounce scattering you can relate with the urban area. Where you have the surface scattering, you can relate with the water body or bare surface, which will have slightly distinct signature of radar measurement. So you can easily distinguish the bare surface where that water body, and that could be useful for the flood or any other damages where the scattering will fluctuate based on the change in the target. Then you can also give the scattering information for your image classifier to classify image or segment the image. Okay, and another important information which is not easily applicable to the optical data. If suppose you want to get that pack information of the any media, for example, you want to get this snowpack parameters, dielectric constant, or suppose you want to get the depth of the snow, or suppose you want to get density of the snowpack. So that will not be easily to get through the optical, because it has the penetration capability in a radar signal. So it will go on some scattering from the pack. And if suppose that scattering information can be related to the physical phenomena like Fresnel transmission equations or Fresnel reflection equation, so then you can invert this dielectric constant, which can be related to the moisture and density. So these are the importance of the extracting of the surface double bounce and volume scattering from the T matrix or another kind of the scattering information. And it's working day night, as you know. That's why we are looking for the radar remote sensing. Okay, so now that you have that this T matrix, and T matrix give the different kind of information, and what are the methods which can represent or present such kind of phenomena. If not so much experts, you can take the different intensity image, make the color coded image, try to interpret your image. It's very basic information. Okay, or suppose you are good in a mathematics, you can also make that eigenvalue decomposition, get that because it's 3 by 3 matrix, you'll get that 3 eigenvalue, and you try to interpret those eigenvalue. Okay, but it is not given like very straightforward interpretation. That's the difficulty of this eigenvalue decomposition. And HV and poly basis have such kind of representation, but it is not representing or not accounting all the polarimetric information is to in these two representation. That another one is, suppose you have that T matrix and you are able to get exact scattering power, volume scattering power, double bounce, surface, helix, and etc. if suppose existing there. So you can interpret this surface scattering. Generally, we say it comes from the boundary of two homogeneous media. For example, air and soil interface. If any scattering is happening, we put in the surface category. Air and water interface, we put in a surface scattering. Okay, so and suppose if any scattering is coming from the inside the media, like for example, signal is penetrating inside the vegetation, so it may go on some depolarization phenomena and will return back. Okay, so we put that one in a volume scattering category. The another one, double bounce. Suppose you have the street and wall interface. One interaction is happening on street, second one is happening on wall and returning to the sensor. So one bounce and second bounce, we are put in a double bounce. So such kind of physical phenomena or physical relations can be fixed or established with the help of the scattering power decomposition. Okay, so you can see that some example how looks. It's a surface scattering based or model based decompositions based image or poly basis image or HV basis image. So you can may like, okay, I like this last one, model based decomposition images, which is representing clear cut of this volume scattering phenomena, and from the caldera of this volcano it's showing this surface scattering, and somewhere maybe you get some red spots either due to the natural dihedral or man-made structure, which is very minor. Okay, there's no much detail of this one. Okay, so you can see that here is a better interpretation of the image comparatively the other two bases. So although there are several models, okay, initially from the 3-component, then it's improved by the Yamaguchi. Okay, so then it's added another component and it's rotated, then extended the volume scattering model. So it's providing for scattering information, surface, double bonds, volume, and helix. But there was some issues which was included or resolved by the G4U by applying the additional unity transformation, because here that all component of the T matrix, there are 9 independent elements were not included and implemented, and it was showing either equally performance of the other existing decomposed or improved one. Okay, so and recently that another extension of the 4-component to the 6-component and 7 components done, but I will show you that established example of G4U here, and then I'll show this 6ST. So in G4U decompositions, you know that you have the T matrix which is coming from the radar measurements, and because in an urban area a lot of states are not orthogonal to the line of sight. They might be oriented from the radar flight, maybe 40 degree, 20 degree, depends on that. And because of that, it's creating that polarization orientation shift. Suppose you are transmitting horizontal, so if it is orthogonal, means almost like parallel to the flight line, so it will produce almost polarized signal. Okay, means you are transmitting H, it will come in H. Or so if suppose you have the orientation of the line of sight from the flight direction, so it will shift that original polarization orientation, and it will give lot of depolarization phenomena in urban area, and which will be mixed with the vegetation phenomena. So it will very hard to discriminate the vegetation from the urban area, which is oriented about the line of sight. So to correct that one, that we rotate the image about the line of sight, and then unity transform that coherency matrix, and we extract this 4 scattering component: the surface, double bonds, volume, and helix. Surface, I told you that it's just appearing from the 2 homogeneous media. Double bonds when it is hitting street wall and coming back to the radar. The volume when it's reaching inside the media, like for example vegetation, snow, glacier, it can produce the volume scattering. The last one, helix is generally compound scattering. It's not like a single scattering information compound. Suppose you have that several target in a line of sight, and suppose it's interacting target 1 and target 2, and all targets within that one resolution cell. So it will create such kind of phase delay which produce the circular power. Okay, although we are not transmitting the circular power, but due to the phase difference between this horizontal and vertical polarizations signal, so we could get this kind of circular power. Okay, due to the compound scattering phenomena. So this is the helix scattering, and we can extract all for scattering power, and we interpret. It's the entire algorithm in terms of the T matrix. Anyone can write. If you don't want to write, it is also available in open access software. It's Pulsar Pro from ESA. Recently they renamed its biomass. So you can get this decomposition tool. You can implement, or suppose someone want to write, it can be written easily, because all elements in terms of the T matrix. So you put here, first you can decide whether scattering is coming from the urban area or coming from the vegetation area by utilizing the branch condition. Once you decide, then you can go one by one equation to solve and get the surface scattering and double bond scattering. So this is very easy. You can implement and get it with different scattering. Like a comparison of different existing approach, like Freeman, Durden, Yamaguchi, original decomposition, Yamaguchi with the rotation about the line of sight. So you can see this, all these are the urban area. Okay, but it has like a mixed classification, okay, or mixed interpretation. Here the seashore vegetation, very short pine trees are there. Okay, so here the vegetation, you can see an optical image, but all these are urban area. and it's showing the same kind of signature. So it's difficult to interpret. So it's improved while he's adding one more component in his decompositions, which is known as a original Yamaguchi component. Then later on, that problem was not solved. Then try to rotate that T matrix about the line of sight, which improved significantly and able to discriminate the vegetation from the oriented urban area. But the problem was that here still we have such significant mix of the volume scattering. Try to develop two volume scattering model. One is specifically for vegetation and one is specifically volume scattering model over the oriented urban area. When we included that one, so a significant improvement we can see urban area classification in comparison to the from the vegetation. So urban area can be discriminated easily from the vegetation area. But all these things, all these decompositions just accounted 6 elements of the T matrix. Okay, so that was the issue which was resolved in a G4U, means a generalized 4-component decomposition of coherency matrix by unitary transformation. So that is giving almost equal results or better, and it's included all the polarimetric information. We are not leaving any polarimetric information which is not included in the decompositions. So this is that one example of the airborne radar system. That this one is the spaceborne loss pulsar. So you can see here San Francisco area, hilly terrain with the vegetation. Here the city, and this area, the green looks like a vegetation, but it is like almost 40 degree oriented from the line of sight. So it is producing significant depolarizations, which is reduced by applying that extension of the 3 to 4 component, then 4 component with the rotation about the line of sight. Then it is by including that extended volume scattering model for oriented dihedral volume scattering model, and which gives little bit improved results as compared to the vegetation. We can discriminate it is not a vegetation. Earlier it was looks like a vegetation here in original decomposition. So this improved interpretation of improved calculations of the scattering power provide a better interpretation and a significant improvement in translating of these results in terms of classification inversion. Okay. Now that how to interpret and what are the candidates for the such scattering phenomena, which are the major or maybe primary candidate to represent such kind of phenomena. Suppose we have that mainly 3 scattering information. Take the double bounce, volume, surface. So as I told that double bounce scattering can be governed over the urban area. Suppose you have a street wall interface. It can be when you have that bridges, fences, and road and fences. Or suppose you have the ship in the ocean, it can give that double bounce scattering like sea surface interaction versus edges of the ship. So such targets can produce the double bounce scattering. And if you are assigning some particular color, if it is dominant in your image, that will be highlighted and you can relate easily. But it can be confused with some target like isolated trees there, that can also produce tree trunk double bounce scattering. Vegetation if in a row, that can also produce double bounce scattering. But you need to get that seasonal changes effect, etc. If that permanent or man-made target, that will not change much in that, or that scattering information will not change much over this permanent target. Permanent means like man-made targets, which is not changing with the time easily. Okay, unless there's any disaster activity. And isolated tree, okay, the tree may show some phenology pattern or may show some changes on the ground conditions, which can show some fluctuation in the scattering. You can get some discrimination from such target from the permanent target. Okay, volume scattering. The primary candidate is vegetation, where the vegetation you will have the significant depolarization, which is translating into the volume scattering and will provide you volume scattering information. And if you are assigning green color, that green color will be reflected in your image. But another candidate is oriented building, which still have some problem. Okay, so if it is oriented, that is also produce such kind of depolarization phenomena, and it's mixed with the volume scattering. But you have to be very careful while interpreting. Other candidate, glacier, oriented surface, snow. These are also candidate for the volume scattering. But location is important. You can decide that where are you looking for looking for whether it's glacier or urban area. So in urban area, for example, you are looking Mumbai, or then you will have some volume scattering that you can relate with the vegetation. If you are looking in Himalaya, okay, there are some kind of vegetation and a glacier. If you are looking toward the glacier generally above the tree line, so you can relate these are the glacier. Okay, so location is that can add you to interpret your images. A surface scatterings may come from the surface of the any media like wet snow, bare soil, water body. You can easily interpret. Okay, so these are the such kind of interpretation which will try to understand now images. Okay, here two images are there. One is pre-disaster, another is post-disaster. Okay, here was Tohoku earthquake in 2011 March, and that one image was captured. Okay, well before this event, and we can see old red area as urban area because double bounce scattering is producing significantly due to this interface of street and wall interface making. Okay, and after this event, you can see significant reduction of double bounce here in this area and this area. It is happening because of if this interface is damaged. Okay, if interface is damaged and just it's converting simply either in debris is covered, okay, or completely wiped out. So it is not going to have such kind of double interface, and it's going and coming back this scattering. Okay, so that's why you are not getting double bounce kind of signature here, and you can relate directly it is happened because due to that damages or wiped out this area completely due to the tsunami force, and either deposited somewhere on the land or retreated back with the tsunami, and which may float in the ocean also, those debris, houses debris. So these are the like very basics and straightforward interpretation of the damages. You can look at if you are able to extract the different scattering information. Changing in the scattering can dictate the change in the target. Your targets are either environmental target or man-made target, means natural target or man-made target, that can let you know the present conditions when you are looking for. Furthermore, it's not here you can also look for the okay, so you can make some automated method also. It's not easy to interpret all the time. You can make such kind of methods which can give automatic extraction or automated way of the extraction where the damages happen and how much the intensity of damages. Okay, this is another example of visual interpretation. In a zoomed up area of the previous image, you can see this area before the tsunami and after the tsunami. So you can see only one or two buildings might be standing here, but rest of that completely wiped out. And another one is the Bay Area. You can see significantly that damages happen, and you can also see some double bounce and scattering is happening here. It is because when its tsunami reached around 40 meters above this area, and while it's retreating, it's bring some houses. Those were floating into the bay. So that's why we can also see that increment in the double bounce, and you can relate and you can identify debris of those houses. Okay, so you understood that how that scattering information is changing and that can dictate the damages. So that can be translated into that difference-based detection of the damages. Okay, so that high, that double bond scattering changing high damages will be there. For example, you look at here, this where the green area almost 10 to 20% damage scattering is changing, and here like partial damages, where that more than 20 to 30% that almost complete damages. Okay, from more than 20%. Like for example, here that complete city is wiped out and deposited somewhere here. So you can relate with this how much that scattering is changing. You can relate the intensity of damages, but you can also see some some kind of increment in the double bounce that could be due to that new construction, or that we can see on the land here. So new construction might took place, and but you can also see here. So there are some retreat of these debris houses along with the tsunami. Those were floating. So you can see the significant increment in the double bounce scattering. So you can also look at the floated debris cover of those houses. Okay, so you can see here more damages or partial damages as a partial, or maybe less change in that scattering information. So scattering informations can dictate us damages changes on the target, okay, which is very useful information, okay, and straightforward interpretation. And suppose you have the tool of such kind of decompositions and images generation. So even though non-experts, people can also interpret where the damages happen. For example, by changing that color code of the scattering information. Okay, so another kind of activities also on the Earth surface is volcano eruption. So you can see here that before the volcano eruption, after the volcano eruption, you can see here the surface means blue color is changing. Blue color means surface scattering is increasing here. And here, because there are like lot of vegetation due to sulfur dioxide, the vegetation died due to the depositions of the ashes which is releasing from the volcano eruptions. Those are also deposited and burned vegetations, and the surface is exposed and having that increment of the surface scattering. So the changing in the surface scattering you can also relate to the volcano eruption and monitor that how much area is damaged of that particular area. Another like forest monitoring is also important for the earth health. So first of all, you can go simply forest, non-forest area by any kind of techniques, optical, or you can look at this SAR data. Okay, so but if you need a regular monitoring, okay, so most of the forests are in the tropical belt, and where that 80% day of the year generally is cloud cover. So you can't get that when this whether illegal logging is happened or it's what is going on. So that SAR system is very good for the tropical belt forest monitoring. And if you have that better tool which can be interpreted by anyone, any agency, so it is always good. So here the one kind of example is given. So you can see here that bare surface, so means no forest, agriculture area, and you can also identify where the more dominant volume scattering, that forest area. And but here you can also see different tone of the green color, which dictating the different kind of forest species. Okay, here more either it depends on the density, depends on that leaf size, etc. It's play an important role. Okay, so you can also utilize scattering information for the and forest non-forest monitoring. So this is the example of the Andhra area. So you can see that there are like hilly regions where some vegetations are on this hilly terrain. So you can see that completely like bare or maybe non-vegetated area and vegetated area. Simple means directly straightforward interpretation. Either you now giving this input to your classification tool, or you are giving this direct some manpower to delineate the vegetation, non-vegetation. Okay. So as I told, this species-wise, we can do the analysis. For example, we have the images over the Haldwani area, Uttarakhand. So we can see that some phenological changes, and the phenological changes are happening in a particular species. Okay, because there are mixed plantation which is showing the non-deciduous kind of nature. There are eucalyptus, so also showing the non-deciduous nature. Only teak is that which is showing the some plantation, this leaf fall kind of phenomena. And as we see here, in month of the December, we don't have such a leaf fall here in the teak plantation, but in March we can see. And because of that, the thinning of the canopy, the signals can penetrate significantly and hitting the ground and trunk interface and producing that different signature. So based on that, we can also distinguish the different forestry species by the scattering nature with the time. You can also see here, this is the mixed plantation, or you can see here that this one is L-band image, this one is X-band image. You can see that frequency is also playing an important role in governing the scattering. So L-band has a significant penetration capability, and this this plantation of the eucalyptus is orthogonal to the line of sight, and which producing significant double bonds. Okay, and here is that Gutel plantation. Okay, it's a kind of significant dense and governing. It's not orthogonal to the radar line of sight, governing the significant depolarization and converting it to the volume scattering. Or the X band, is attenuated at the surface of this plantation, and it has some significant penetration in eucalyptus, but not as we can see here in L band. So we are governing significant volume scattering. So the frequency, multi-frequency can also play an important role for identifying the scattering informations, which can be utilized for the species identification. Okay, another example of double bond scattering. So you can see a lot of ships and the sea in the ocean area, and you can see that based on that intensity, size, you can see that whether it is small vessels or big ship. So you can also do that detection of ship based on the scattering power. Another important thing, so aquaculture. Okay, a lot of aquaculture is happening in the eastern countries, and you can also monitor based on the scattering change phenomena. Here you can look at, it's not significant, just aquaculture site here, but when the structures are well established, and it's showing that a very kind of specular reflection of the radar scattering. So, or radar energy, or incident energy, it's going away from the sensor. Why it is happening? When you put the structure, so there are like ocean waves that hitting those structures, and it is a little bit calm compared to the surrounding area, and it will show like very smooth surface as comparatively outside. And when it's leave this structure area, again it will mix with the high wave area, and this particular structure area will show as specular reflection kind of phenomena, and you can easily identify where the aquaculture sites are. Another, like you have that abundant river course, you can easily identify based on the signature. You have that very old course of the river here, which is showing such kind of volume scattering, because that signal is penetrating inside and governing some interaction with the bed and coming back with the high return. How the surrounding area has such villages, some moistures is different from the river course, and it's giving that distinct pattern. So you can easily identify that abundant river course. And this is the L-band signal, L-band data. L-band has a significant penetration capability and will show such kind of phenomenon. So another example, okay, so we can also do some glacier identification. Okay, so also here you have that Gangotri glacier here. Optical image, generally snow cold area reflect that most of the energy, almost 80 to 90%, 90 more than 90%. If it is like not contaminated snow, so and it's reflect most of the energy back to the atmosphere, and in optical image it's appear like a very bright, okay, like white color. And where you have the debris covered or ice it's covered with the soil and boulders have the low albedo. And where you have some kind of transition converting snow to ice, okay, so that will have like intermediate albedo between snow and ice. Okay. So the same phenomena we can also capture with the help of the radar images. You can see where are that glacier with the debris cover, which is producing significant roughness on the surface. That is also cause of the depolarization phenomena. And while it penetrating inside the ice and causing volume scattering, so it have that volume scattering dominant area, particular in debris covered ice, where you have that transition zone converting from snow to fun area. Okay, then we will have a mix of the surface and volume scattering. And we have that because this image in month of June, generally snow become very wet. Okay, so it will have like a surface scattering, because in wet snow the radar signal will not penetrate, it will interact air and snow interface maximum and will return to the sensor. So surface scattering is dominant. So based on this scattering information, you can also get that snow condition, whether it is wet or it is in like moist conditions or in a not in a wet condition. If you are not detecting dry snow, generally signal penetrate, and there's some dry snow will appear as a transparent layer to the radar signal, so you will not get any much interaction with the snow. But when it's change that dry to wet snow, drastically change, and the entire energy interact with the surface and will return. So you can see here between this transition zone, you have that equal significant amount of surface and volume. As it's reached into that wet snow zone, the surface scattering is dominant and volume is very low, less than 10%. So you can identify. Another condition, you can also look at the changes of the snow. Suppose you have the snow covered area, and after some days that warming is there, or maybe that higher temperature or warm temperature is there, so it will melt, and you can see this significant reduction of the snow. This area, all blue area in that Mount Iwate, then you can see the significant bluish area is wet snow. And after 46 days, when we took then another image, so we have the significant reduction in the snow. So we can also get that how much the snow is accumulated and how much with the thickness. If we can get the snow water equivalent, it will be very good for the various agencies, including that irrigation purpose, hydropower industry, okay, and other agencies. Okay. So how much time I have? Okay, I'll try to finish as soon as possible. So that recent development which we are doing, so based on the scattering information, we can also invert those parameters. Okay, like for example, from the snow, we generally consider the volume and surface will be dominant. We can tune that these scattering parameters, and those parameters of the snow grain size will be spheroidal. Okay, so then we can change that model and we'll get it this dielectric constant. We can retrieve the dielectric constant and convert into the density. Some inversion of the physical property of the target can be done. This is the another, like you heard about the 4 component. Okay, recently that we interpreted more parameters which dealing the compound scattering phenomena, oriented dipole and compound dipole, and extended this 4 component to the 6 component, which just avoided such kind of orthogonal oriented urban area problem from the vegetation, so we can significantly improve. Okay, so these problems is avoided in a recent one decomposition. So we are working here more development of the 6SD decompositions based applications, which will come up soon. Okay, in conclusion, you learned that polarimetrics are based methods are good, okay, which can provide very good information for monitoring the earth surface. Okay, so which is very good to relate to that monitoring of the earth surface for the disaster or some slow changes or rapid changes, and it's work in a day night. So these are the advantages of the polarimetric source which you learned here, or we discussed here. Okay, and I thanks to this man who was that motivator of the polarimetric sensors and encouraged that several agencies to build that fully polarimetric sensors. Now that he is no more with us, but he might be listening us. Okay, so I thanks his effort what he made and where we are today. Okay, so if you look at that more images of the pulsar, so you can visit my site, you will get more applications of the 6 component decompositions, because time was limited here. So thank you very much for your patience.